Hello and welcome to T Academy. The topic of today's discussion is response of LTI systems to complex exponentials. So we have already discussed in our previous lecture that if we have an LTI system, linear time invariant system, and if we apply an input x of t to this system, which is an eigen function of the LTI system, then the response that we get, y of t, is simply a scaled version of x of t. And as a particular input, we saw that the complex exponential e to the power st is an eigenfunction of the LTI system. So if this is applied, then the response that we get is h of s times e to the power st, where h of s is known as the eigenvalue associated with the eigenfunction e to the power st, and we derived the relationship to calculate h of s, which is given as minus infinity to infinity h of tau e to the power minus s tau d tau, where h of tau is the impulse response of the system. So in other words, if we know the impulse response of the system, we can find out the eigenvalue associated with the eigenfunction e to the power st and find out the response y of t. So we went further from that in the previous lecture, and we established that if we have an input x of t, which can be written as a summation of complex exponentials, so a1 e to the power s1t plus a2 e to the power s2t plus so on, then the response y of t is simply the coefficients associated with the input x of t times the eigenvalue associated with that eigenfunction plus the coefficient associated with the second input times the eigenvalue associated with the second input plus so on. Thus, in a nice closed form, we can write x of t, that if x of t goes from k equal to 1 to n ak e to the power sk t, then the response of an LTI system will simply be k equal to 1 to n ak h of sk e to the power sk t. So till now this was just a recap of my previous lecture on eigenfunctions, eigenvalues and their relationship with Fourier series. So in today's lecture we will use this relationship to find out the response of an LTI system y of t to this input x of t minus 3. So this is a very simple delay operation which I covered in one of my first lectures on this tutorial series on signals and systems. So you can watch the lecture by clicking the link if you are interested. So if this is the relationship between the output and the input, and I know that the input is a summation of two cosine functions. So cosine of 4t plus cosine of 7t. Then very straightforward from here, I know that the response of the system will be cosine of 4 times t minus 3 plus cosine of 7 times t minus 3. However, we want to use the properties of eigenfunctions and eigenvalues in order to derive this relationship. So let's get started. First of all, I will write my input x of t as a summation of complex exponentials by using the Euler's relation. So the term cosine 4t can be written as e to the power j 4t plus e to the power minus j 4t divided by 2, and the term cosine 7t can be written as e to the power j 7t plus e to the power minus j 7t divided by 2. So if you don't know how the Euler's relation is derived, you can watch my lecture on Euler's identity where I derived this relationship. Next, I want to write this input in this form. So I want a coefficient times the eigenfunction. So I know this complex exponential is an eigenfunction, so I can write it more conveniently as half, which is the coefficient of this eigenfunction, times e to the power j4t plus half e to the power minus j4t plus half e to the power j7t plus half e to the power minus j7t. So from here I can see that I have 4 frequencies in my system where S1 is equal to J4 and the coefficient A1 associated with S1 is half. Similarly, I have S2 is equal to minus J4 with A2 equal to half, S3 as J7 and A3 again as half, and S4 equal to minus J7 with the coefficient A4 is equal to half. So once I know this, the only thing left is to calculate the eigenvalues associated with these inputs. So let's proceed to find that. We know that the eigenvalue h of s is given as minus infinity to infinity h of tau e to the power minus s tau d tau, and we have the relationship between the input and the output, that the output y of t is equal to x of t minus 3. We know that if we want to find out the impulse response h of t, then we simply substitute delta as the input. So the impulse response h of t is equal to delta of t minus 3, which I can substitute here. So my eigenvalue h of s will be minus infinity to infinity delta of tau minus 3 e to the power minus s tau d tau. Now using the shifting property, the shifting property of the delta function, we know that this integral exists only at tau equals to 3. Thus, the eigenvalue h of s is simply equal to e to the power minus 3s. Once I have h of s, I have to find out the eigenvalues associated with all these frequencies, h of s1 to h of s4. So let's find out these. So h of s1 will simply be e to the power minus 3 times j4. We have e to the power minus j12 as the first eigenvalue, and the second eigenvalue will be e to the power minus 3 times minus j4, which will be equal to e to the power j12. Then h of s3 will be e to the power minus 3 times j7, which is equal to e to the power minus 21j. And finally h of s4, which is equal to e to the power minus 3 times minus j7, or e to the power 21j. So now we have everything we need to construct the output signal y of t. We have the eigenvalues and we also have the coefficients of the input, thus we can construct the output. So the output y of t can be written as the coefficient a1 times h of s1 times e to the power s1t plus a2 h of s2 e to the power s2t plus a3 h of s3 e to the power s3t plus a4 h of s4 e to the power s4t. Now plugging in the values, we know that a1 to a4 are all equal to half. So half h of s1 is e to the power minus j12 times s1 is equal to j4, so e to the power j4t plus half e to the power plus j12 times e to the power minus j4t. a3 is also half. H of s3 is e to the power minus 21j, and e to the power s3 is j7. Plus a4 is again half. H of s4 is the complex conjugate, so e to the power 21j, and s4 is equal to minus j7t. This is also a t here. Now we can simplify this expression a bit more. So taking half common from the first two terms, so taking e to the power j4 common, then inside the brackets I have t minus 3 plus, now taking e to the power minus j4 common, so again in the brackets I have t minus 3. Taking half common from these last two terms and taking j7 common, inside the brackets I would have t minus 3 plus e to the power minus j7 t minus 3. So this again is nothing but the Euler's relation for cosine of 4 times t minus 3, and this is cosine of 7 times t minus 3. So this is the output y of t, which we have derived using the properties of complex exponentials being the eigenfunctions of LTI systems. So this property of complex exponentials being eigenfunctions of LTI system will be extremely useful when we will do frequency domain analysis. So that's it for today's lecture. I hope the content of today's lecture were clear to you. Stay tuned and I'll see you again in another lecture. Bye.